So thanks again for the invitation to speak. It's fun to be here virtually. This work is done with Simon Noppen and student Dongzhu. And the background is so long-standing interest in looking for long-lived particles at the Large Hadron Collider, the LHC. So one might ask, why are long-lived particles at the Large Hadron Collider such an interesting topic? And there's a certain obvious answer that you might have in the back of your mind, which is we've looked for new physics everywhere else at the LHC and we haven't found anything. So this area is relatively understudied. Let's look over there. In other words, you turn over all the stones that you can. That's a major oversimplification. There's some truth to it, but one prompt search, oh shoot, I thought I fixed that, is not equal to one displaced search. The really phenomenal power of searches for long-lived particles at the LHC is that standard model backgrounds tend to die off exponentially fast with the lifetime of the decaying particle. So for instance, this is a particularly clean demonstration of that general observation. This is taken from a search done by CMS for displaced muons. The displacement of a muon is, like the displacement of any charged track, characterized by its impact parameter, its transverse impact parameter relative to the beamline. So if you track the reconstructed track back and extrapolate the transverse impact parameter that characterizes the displacement of the track is measured from the shortest distance between the track and the beamline. So in particular, one thing to be wary of is the transverse impact parameter that characterizes the displacement of a track depends in part on the angle that a track makes, not just the displacement of the point where it's born. If you just have one track, that's the best you can do. Of course, if you have two displaced tracks that meet at a particular point, that gives you a vertex that you can position. So here, as a function of the transverse impact parameter d naught here in centimeters, you can see what the standard model backgrounds look like. So this is a log histogram here, and so you can see the backgrounds for displaced muons fall off exponentially quickly with increasing lifetime. So they're dominated largely by the actual semi-long-lived particles in the standard model. So tau has a finite lifetime. The B quark is included in the heavy flavor here. Has a longer lifetime. And once you get out beyond those backgrounds, there's essentially no physics background to this signal. This is very unusual for hadron colliders because hadron colliders are typically enormously high background environments. That's why it's easier to look for heavy things than light things at the Large Hadron Collider because you can control the backgrounds, the standard model backgrounds, by going up to very heavy masses. But you can also control standard model backgrounds by going out to large lifetimes. And that's phenomenal because low backgrounds means you can be very sensitive without having to make a ton of very specialized cuts. So what this means is displaced searches are often fairly insensitive to the specific details of the decay. If you're looking for a vertex that is a so-called displaced vertex, where you have a whole bunch of displaced tracks that meet at a point, you don't need to specify whether there's 2 jets or 3 jets or even just one particle decaying to a bunch of tracks without any particular jettiness involved. You can just say, hey, I found a displaced vertex with some number of charged tracks. And that means you can do one search for a displaced vertex and interpret the results in a wide variety of different models without having to run separate searches for all those different models. So unusually for a Hadron Collider search, looking for long-lived particles can give you typically powerful and inclusive searches. So this is the great advantage of long-lived particle searches at the LHC. And besides the practical reasons why long-lived particle searches are different from prompt searches, we also have a lot of reasons to think that it's actually fairly well motivated to look for new physics with long lifetimes. For instance, the simple fact that we've looked for new physics that is prompt, and we found only the Higgs boson and nothing beyond the standard model, very often pushes new physics into regimes that naturally give you long-lived signatures. For instance, and this has historically been some of the earliest interest in long-lived particles, if you start out in the context of supersymmetry and say, hey, I have a relatively heavy Higgs mass up at 125 GeV, and now that the LHC tells us that the colored superpartners in particular have to be fairly heavy compared to the Higgs scale, then for a variety of reasons, you might expect some of the superpartners to be long-lived. For instance, if supersymmetry is a little bit tuned, then you might predict that the scalars in particular are heavy, but the supersymmetric partners of the fermions are light. This is called the mini-split scenario. In this case, you would produce things like, say, few TeV gluons, and their lifetime would be suppressed by say 20 TeV squark lifetimes mediating this decay. Or if you're in gauge-mediated supersymmetry breaking and you want heavy superpartner masses, you have to crank up the supersymmetry breaking scale, and that suppresses the couplings to the gravitinos. Perhaps more compelling, the idea of neutral naturalness is suggestion that instead of looking for colored particles to fix up the hierarchy problem, maybe you should be looking for neutral particles, in which case the leading signature of this class of models to address the hierarchy problem is actually Higgs decays into dark gluons, which go on to shower and hadronize into composite dark hadrons that decay via higher dimension operators and a small Higgs mixing. That also naturally gives you long lifetimes. Besides the hierarchy problem, of course, cosmology, always you turn to cosmology to get motivations for beyond the standard model physics. So if you care about the matter-antimatter asymmetry, for example, if you have a baryon asymmetry and you have R-parity violating couplings, say of squarks to jets, then you require that to be sufficiently small not to be in equilibrium in the early universe. That gives you a natural reason to expect squarks to have displaced decays. And of course, there's an infinite number of different ways you can get long-lived particles out of dark matter model building, limited only by your creativity. Some well-motivated examples are, for instance, the freeze-in rather than freeze-out of dark matter. In this example, you have a new species, B, that lives in the radiation bath with the standard model, and that has a very small coupling to dark matter such that you freeze in the right relic abundance. This tends to give you a macroscopic lifetime for B because this coupling is required to be small. Other reasons to get long-lived particles might be co-annihilation. In this case, you have dark matter and it has a partner particle X. It has to be X and chi have to be close together in mass so that X and chi are both involved in the dark matter freeze-out process. But then that necessarily squeezes the phase space available for a particle X to decay, and that naturally gives you displaced signatures. These are just some examples. Part of the point to take away from this is if you go through the list of motivations for long-lived particles, and in particular long-lived particles at the LHC, some of the earliest motivations came from perturbative theories, in particular supersymmetric models, and models of dark matter, often supersymmetric dark matter or dark matter mechanisms that sort of abstract a lot of the ideas about how WIMP dark matter and SUSY works. That history informed an awful lot of the experimental search strategy for long-lived particles. But long-lived particles are even more generic and even easier to realize in confining theories. For instance, the Standard Model has lots of long-lived particles, and most of them, not all, but most, are hadrons. You know, the neutron, K long, B and D mesons. And there are two main reasons why you get long lifetimes very generically in confining theories. One is that composite states, which describe the hadrons after confinement, decay to the Standard Model through high mass dimension operators. And so the decays are therefore suppressed by potentially large powers of the confining scale over some other mass scale, which is typically higher. Then the other main reason, for instance, apply that to these cases. You have, for instance, for B mesons, you have a B mass scale, but you also have the QCD scale. It's a raise factor of 5. You square that, you get 25. You raise that to a fourth power, you're talking orders of magnitude. But another big factor, which is responsible for a lot of the long lifetimes in the Standard Model, are accidental global symmetries. These can be discrete. For instance, they could be CP, like what gives the K long its very long lifetime, or it can be approximate flavor symmetries. The Standard Model pions are an example of how an approximate flavor symmetry can substantially change your expectations for the lifetimes. The charged pions carry isospin, which is broken explicitly by the weak bosons, and therefore when these pions decay, they do so through a dimension 6 operator, which gives their decay matrix element and a suppression of a small mass scale, typical of the confining theory, over the scale of the interaction, the heavy interaction that is responsible for breaking the flavor symmetries. The matrix element goes like this ratio squared, so the decay goes like that to the fourth power, so that's a strong suppression. But the neutral pion, the flavor symmetry is anomalous that sees the anomaly, and it can decay through a dimension 5 operator, and therefore much more rapidly than the charged pions. So getting sort of accidental approximate global symmetries in confining theories is fairly generic. Just sort of, you write down your matter content and you very generically get approximate global symmetries. This combined with the composite nature of the particles that are decaying means that very generically, almost without needing to worry about exactly what mass scale you have in your confining theory and what scale operator you have for the decay, it is very common to have at least one particle that has a detector relevant lifetime. So the characteristic features of production of these sorts of confining events have often called dark shower events. Exactly what people mean by dark shower sometimes depends on who's talking, and I will define very concretely what I mean by dark shower for the purposes of this talk in a little bit. But the characteristic features of producing events in a confining hidden sector as opposed to producing pair production or single production of states in a perturbative model. For one thing, you have a variable and potentially large object multiplicity. So you have the same underlying partonic process. Say you produce two heavy fundamentals of your dark age group. What actually shows up in your detector is going to be a number of dark hadrons that depends on the details of showering and hadronization in the dark sector, and you will get different numbers of visible objects, event by event. You will have non-standard model-like distributions of both energy, so the spatial distribution of energy in the event, as well as the flavor of the standard model objects that you expect. So you expect something that looks quite different from QCD. So on one hand, that's very good. On the other hand, this is where some of the most model dependence comes in. the objects that you produce are very often not isolated, either from each other or from, so in particular, some of them are displaced. The displaced objects may not be isolated from each other, and they may not be isolated from stuff that decays promptly. Finally, there's a hierarchy of predicted lifetimes. You expect to produce particles that have a wide range of different lifetimes, because you expect hadrons with a wide range of different flavor, CP, and mass dimension in the operators that describe them. So when you put these together, you get a very different set of considerations for designing a long-lived particle search program than you do when you're thinking about single or pair production of long-lived particles, which are much simpler to think about, are well motivated by Susie, and now experimentally are under fair amount of, I'm a theorist, so it's easy for me to say this, experimentalists are on those signatures, they're working on it. There's room for improvement. The searches are very hard. And so it takes a lot of work to produce those searches, but as a theorist, like, oh yeah, they've got it covered. So the questions that I think it is most interesting for theorists to be thinking about in terms of making sure that the LHC physics program realizes its full potential is understanding how, given these features of dark shower events, we can make sure that there are searches in place that can detect these kinds of non-isolated, large and variable multiplicity events that feature both potentially prompt, displaced, and detector stable objects. And not only that, but also produce the results in a way that allows us to interpret them in a sane way and apply them to a range of different models, because the model dependence in these kinds of signatures is enormous. So some work on dark shower type signatures have covered some subclasses. So for instance, one well-motivated class is what's called so-called semi-visible jets, terminology from this group. The idea here is you have a dark shower and you have essentially two kinds of particles. You have some that decay promptly to standard model stuff, and you have some that are detector stable and just escape the detector as missing energy. In this case, you have jetty events. So it looks basically like standard model-ish jets, but an order one fraction of the particles in these events escape the detector. So concretely, there's a model that realizes this, where you have a new Z prime mediator that allows you to pair produce dark quarks. These ultimately shower down to dark pions, and the detector stable particles are the pions that carry the dark flavor symmetry, and the promptly decaying ones are the ones that are diagonal under the flavor symmetry. So the major conundrum, let me get to that in a second. Another class of models are so-called emerging jets. Idea here is very similar, except now the lightest dark hadron, instead of being detector stable, now has a detector scale lifetime. And so this model also does not have any promptly decaying particles. So you make a jet of particles, and then they're invisible to your detector until the metastable particle starts decaying. And so you get this so-called emerging jet as the particles travel through the tracker. The model in the literature is controlled by a pair production of particles that are charged under both our QCD, so they have to be fairly heavy. And these particles also carry charge under the dark gauge group. So that these bifundamentals also mediate the decay. The important issue, feature of these kinds of models is that the paraproduction proceeds through QCD. Therefore, it necessarily has to happen at very high energies with additional handles on the event from pure QCD rather than the displaced objects themselves. Something to keep in mind here when we're talking about generic signatures of these confining sectors, the detector signature will involve some combination of promptly decaying species, things that have a detector scale lifetime, and particles that escape the detector. If you only have prompt things and missing energy, then you can fold a lot of the theoretical uncertainty in predicting the signals into just a phenomenological parameter, how many of your particles are stable and how many are prompt. But as soon as your detector signature relies on knowing the typical production rate for displaced events in your detector, this is a theoretical headache because it means the objects that you want to look for in the detector are inextricably tied to the predictions for the multiplicity of a specific given dark hadron species. That is not so nice if you're a theorist, because the multiplicity of a specific hadron species is not an infrared collinear safe observable. It is something that is inherently non-perturbative. So it's enormously sensitive to the details of the non-perturbative hadronization process, which means that we don't have the tools to model it carefully. In QCD, we have over decades developed Monte Carlo tools that we tune to data to reproduce observed data, and still every time we move into a new kinematic regime, we have to retune the Monte Carlo tools to match the data. And that's QCD. If we have now a non-standard model theory where we have to guess at what the spectrum is, and the hadronization dynamics may be very different from the ones that we know in QCD, our predictions for the multiplicity of any dark hadron species are going to be very poor. So on one hand, the fact that we, in these theories that predict a large number of displaced objects, give us what in principle should be an extremely clean detector signature. So on one hand, you want to exploit the fact that you have a theory that gives you a large number of displaced objects because your standard model background will be very small. So experimentally, you absolutely want to absolutely want to go after that signature because it is a prime discovery channel. On the other hand, understanding how to approach these analyses is very challenging from a theoretical point of view, because the discovery signature is something that forces us to confront the hadronization uncertainties in our models head on. We can't get around that. We have to make toy models and accept that they're toy models, and then understand how to use those toy models in a way that is scientifically productive. To make things worse, the existence of jets is an expectation that's inherited from QCD and is not representative of a generic confining hidden sector. So jets are what you get when you have a perturbative parton shower for a substantial portion of evolution. The 't Hooft coupling, which is g squared times the number of flavors, is the quantity that determines whether or not a perturbative description is a good one. When the 't Hooft coupling stays large over a extended range of energies, then you get, instead of these sort of narrow jetty distributions of energy, You instead expect more spherical events because at large at hoof coupling, wide angle emissions are no longer parametrically suppressed compared to small angle and soft splittings. So there is some work on event generation for so-called SUPs in the spherical regime, but the question remains, what if the at-hoof coupling is just sort of order 1? What if it's not extremely large and not extremely small, like in QCD? What if it's moderate? There is no good theoretical understanding of what the spatial distribution of energy should be like in confining theories in this regime. There has been some preliminary work on basically constructing toy models that interpolate between the very spherical like events at large at hoof coupling and the more pencil-like events in the QCD-like regime. And this is, again, it's a toy model. The reason to have these toy models and like them is they give us reality checks on how sensitive searches can be that are not to either this regime or this regime. Ideally, you start developing searches that use the tools you have and exploit the inclusive nature of long-lived particle searches to guarantee that you get coverage even in regimes where theoretically our predictions are very poor. But in order to actually validate that, it's very important to have toy models that interpolate between these regimes to check that expectation. So yes, we have a lot of trouble making good predictions for showering and hadronization in non-QCD-like models. And if we want to really maximize the discovery potential of the LHC, we need to understand what our theoretical known unknowns actually are in order to make sure that they don't stop us from discovering physics that might live there. So that's the background for the program that we have in this paper. So the idea that we have is we want to develop tools that will enable experimentalists to start doing a systematic search for dark shower events. And what we mean for this purpose for dark showers are objects that have roughly 3 or more displaced objects per event. The reason for this is signatures that have 1 or 2 displaced objects are fairly well covered by now by existing strategies, even if not by existing searches. So people are working on this. But for 3 or more displaced objects per event, you're really in a different regime for 2 reasons. 1, because adding more displaced objects suppresses your backgrounds. And so these are often very clean signatures, which means you don't have to make a lot of cuts. And that's extremely good because the kinds of signatures that populate, the kinds of models that populate these signatures, we have a great difficulty in predicting exactly what they will look like in any given model. And so the more inclusive the search, the better. You're sensitive to more models and you're less sensitive to grotesque failures of theoretical modeling in any specific theory. So the strategy that we're going to use, basically by necessity, we're going to use QCD-like benchmarks. So in particular, benchmarks that have parton showers and have hadronization spectra that are not terribly different from QCD, partly so that we know we're doing something relatively sensible, and largely because those are the tools that are best developed. And any benchmark that you can use for an experimental search program has to be able to have Monte Carlo event generation where the experimentalists can't do the search. So we'll start out using the tools we have, but we will always be emphasizing inclusivity at the analysis level. And then the big picture is that using these benchmarks, we can assess the sensitivity to these multi-displaced object events, you explicitly verify the expectation that the low standard model backgrounds means you don't have to worry about the detailed spatial distribution of these objects. And you can report the results in a way that allows for easy interpretation in a range of models, which addresses the major theoretical uncertainties. That's the big picture. So a dark shower event you can think of as being broken into three pieces. The production from standard model particles, you initiate the shower by producing objects that are charged under the dark gauge group. There's this process of evolution in the dark sector, where in a QCD-like theory, you have a separate phase of parton shower, followed by hadronization. And then the dark hadrons decay. So production and decay, these steps that involve communication of the the new particles with the standard model, we understand those relatively well. It's this process in the middle where you have non-perturbative dynamics in the hidden sector that is where all the issues and all the headaches come in. So for production, we advocate as a primary focus that the most interesting way from the point of view of designing a maximally sensitive search program at the LHC should be production in decays of the standard model Higgs boson. One reason for that is the particle that you're using to produce the dark stuff, we already know it exists, that's a plus. We also know an awful lot about its properties. In particular, it sets a characteristic mass and a maximum cross-section for these events. The main reason why it's interesting to focus on the standard model Higgs is because it is a relatively low mass signature. That means it is a challenging benchmark for both trigger and analysis development. If you can find dark showers produced in Higgs boson decays, then we think this is again something that needs to be backed up with detailed experimental checks. You should be able to pick up dark showers initiated by heavier mediators as well, because the Higgs, the low energy, the soft long-lived particles that are produced in these relatively low energy events, if you have a search that is capable of picking up such low energy things, then you are well primed to pick up the relatively easier targets when production comes in through a heavier mediator. Another advantage of considering standard model Higgs boson is that even if you can't solve the hard triggering problems on the displaced stuff itself, there's always a fallback because the Higgs production in association with a vector boson that decays leptonically gives you a built-in trigger through the lepton decay of the vector boson here. So that would at least let you do analyses in this case, even if the triggering is out of reach. However, because standard model Higgs is a fairly challenging benchmark, especially if you're trying to trigger directly on long-lived particles rather than on the associated standard model objects, we also have developed in the benchmark models that we're going to present production via a new mediator. And unlike some but not all of the models in the literature, we advocate using the production through the S-channel mediator for the reason that in these models, what the final state looks like is possibly initial state radiation, but then the final state particles are just the dark shower itself. There's no associated standard model object. And that's distinct in particular from the T-channel emerging jet model that CMS has already done a search for. that means that this choice, and why we are advocating for this choice of S-channel production, is because the trigger and analysis in this case really have to focus on the displaced objects themselves. And that is a challenging benchmark for experimentalists, because looking for displaced objects is much harder. So I just realized I didn't explicitly say this. In case you didn't know, displaced objects are not what the LHC was designed to see. And so you have to work much harder to reconstruct them. You're using your detectors in ways that they weren't originally designed to be used. And so that's harder, especially at the trigger level, because then it has to be done at a hardware level rather than an analysis level. But if you can't trigger on these displaced signatures, then you're leaving a lot of new physics on the table. And right now is when a lot of work is being done on triggers for the HL-LHC. So this is the right time to be suggesting new benchmarks for triggering. Right. So the shower. This is the ugly bit.
Excuse me.
Yes.
So may I ask a question for the previous slide?
Mm-hmm.
Yes, see. So here, if we produce a highly boosted Higgs,
Mm-hmm.
so is it helpful for the trigger and analysis?
Yeah, it can be. It depends in particular on how boosted you need to be. Because if you have V Higgs, you have a trigger built in at about 1% of gluon fusion rate.
Yes.
So whether or not you beat this, given the boost, depends how much of a boost you need.
I see. Okay, thank you.
Thanks for the question. All right, so we're using the PYTHIA Hidden Valley module because this is the tool that we have. This Hidden Valley module contains N-flavor QCD, but it contains a truncated set of N-flavor QCD. We've set N equals 1, not because we are trying to really describe real single flavor QCD, but because N equals 1 in the PYTHIA 8 Hidden Valley module is a useful toy model. I want to be very clear. We don't think we're really doing N equals 1 QCD. We are setting N equals 1 in PYTHIA 8 Hidden Valley and using that as a useful toy model to capture the essential signatures of a broader set of theories. So there's QCD like parton shower evolution and a QCD informed hadronization model. The big difference between PYTHIA 8 Hidden Valley and full QCD is that the hadron sector is very minimal. It contains two different kinds of mesons. It contains a spin 1 meson and a spin 0 meson. If you set N equals 2, then these will carry flavor quantum numbers as well, but you still only have spin 0 and spin 1 mesons. But something that is non-QCD-like about the hadronization model is it does not allow you to parametrically separate the spin 0 meson from the confinement scale in the hidden sector. So you can't really self-consistently use it to describe Goldstone bosons. We use this hadronization model to give us one meson that decays to the standard model and one meson that doesn't. What happens to the meson that doesn't decay to the standard model is something that we offer basically two settings. You can have one setting where the meson that doesn't decay to the standard model is in fact detector stable and therefore leaves the detector, shows up as missing energy. Or you can have the other setting where the meson decays to the other meson that then ultimately goes into the standard model. So we set it up so that the spin 1 meson can decay to pairs of the spin 0 meson if that is kinematically accessible. And so if you change the meson mass hierarchy to either open or close that decay channel, that gives you a switch to control the multiplicity of your visibly decaying particle. I want to emphasize, this is a toy model. This is a way to use the tools that, the Monte Carlo tools that we have to scan the non-perturbative quantity of detector interest, which is the specific multiplicity of a meson species with a detector scale lifetime. But it should not be taken literally. So back on more solid ground, we can talk about the decays of dark mesons to the standard model. Choosing which operator you want to consider as the leading operator connecting the dark sector to the standard model is going to determine what the decays actually look like in the detector, both the kinds of objects that appear in the standard model, as well as the typical lifetimes that you expect as a function of decaying particle mass. So we consider 5 benchmark portals. The guiding philosophy that we used is we considered operator dimensions up to 5, so we're normalizable as well as dimension 5 couplings, but without any new sources of flavor violation. So that's the reason we didn't consider the neutrino portal, because that requires new flavor violation. Those considerations give us the first 4 models. And then we added one model that is in sort of close analogy to standard model neutral pion decay. We added in an explicit light-dark photon that couples to the dark spin 0 meson the same way a neutral pion couples to pairs of photons, and then let that dark photon decay via kinetic mixing. So the kinds of final state objects you get depend in detail on the decay operator. So for the gluon portal, we let the spin 0 particle have an axion-like coupling to gluon field strengths. So you get decays to hadrons, basically. So you get displaced vertices with multiple tracks, all hadrons, no leptons. Similarly, you can have an axion-like coupling to photon field strengths that gives you photon shower. You can couple the vector meson to the strictly hypercharged field strength, photon field strength at low masses, via kinetic mixing. That lets the vector meson decay to combinations of either lepton pairs or multihadrons, depending on the mass. In this case, because the scalar, the spin 0 meson, is typically lighter than the spin 1 meson, the spin 0 meson will be detector stable, and so you will almost always get a lot of missing energy in this particular case. Higgs portal will give you heavy flavor rich signatures. And then the dark photon portal, it's actually the dark photon here that gives you the long lifetime rather than the dark mesons. And that gives you hadrons and leptons according to the branching ratios of the dark photon. So this gives you, yeah.
Excuse me. So in the Higgs portal case, what is the field phi?
Good, yeah. So
tilde or?
Yeah, it's our spin 0 meson in our toy model.
Other than eta tilde.
Yeah, it's another eta tilde. In order to have this coupling, you need either CP violation, or you need to have a scalar meson. So there are non-standard model-like theories that have scalar mesons. You can get this, for instance, in one flavor QCD, real one flavor QCD, where the sigma is narrow. Or you can get it if you have, say, scalar rather than fermionic constituents. I'll talk about that in a moment.
Thank you.
So the idea here is that we have a wide range of different detector signatures. And part of the motivation for studying all these models is that they give a range of objects that can hopefully help flesh out experimental sensitivity to a wide range of detector signatures. So light-dark mesons are generically long-lived. There's an asterisk there because there's a lot of theoretical assumptions that you have to be mindful of making in making this statement. And there are a variety of reasons why light-dark mesons end up being long-lived. One is that there can be experimental bounds on the sizes of the portal couplings involved in making them decay. Another one is if you have a effective operator governing the decay, ultimately this needs to be UV completed in a realistic theory. And there's often some model building limitations on the masses of the new particles that you would need in a UV completion in order to generate those portal couplings. And then again, yeah, you're describing the decay of composite operators, and that gives you additional mass suppression. So it's easiest to illustrate these kinds of considerations with an example. So let's consider the gluon portal. So here we have in this, in the infrared theory, a scalar meson talking to a pair of gluons. This is a dimension 5 coupling, so there's some F eta suppressing this decay. If I think about where this is coming from in a UV completion, I've got a composite state, so pseudoscalar made out of a bound state of a pair of fermions, which maps to the eta tilde, sorry, there's a tilde missing, times the strong coupling confinement scale squared. Then I can generate this kind of GG dual coupling by having a loop of colored fermions talking to a fundamental pseudoscalar here. When I integrate out these heavy fermions that carry color, I get one on their mass scale in the matrix element. Integrating out this heavy pseudoscalar gives me another propagator here, and then Yukawa couplings to both the meson constituents as well as the heavy colored charged particles. So at the end of the day, that gives you an idea for your suppression scale that depends on the ratio of your meson mass scale, essentially, to the fundamental pseudoscalar. And then you have some heavy colored stuff. So if you take the bounds on heavy colored fermions from the LHC, and you don't bend over backwards to try to live in the margins, you just say, okay, they can't be lighter than about 2 TeV. That's generic result. I don't want my Yukawa couplings to be non-perturbatively large, and just for definiteness, we'll take 1 generation worth of these quarks. Plug that in here, calculate the decay rate that follows from the particular suppression scale in this operator, tells you that the lifetime of the eta through this decay is 7 centimeters for a fundamental pseudoscalar at 500 GeV and the scalar at 5 GeV. So depends very strongly on the mass of the eta because again, it's a composite operator, you get very steep mass dependence. And it also depends on the mass scale of this new mediator. So this isn't, so when I say, there's a lower bound on the reasonable lifetime for these, this is not a, hard experimental bound. This is, I would have trouble constructing a sensible UV completion that gives me a smaller lifetime unless I try very hard to get around this bound or try to come up with something more clever for connecting the composite state to the colored particles. A different example, in a different sort of set of considerations, comes in for the vector portal example. So again, here we have a vector meson that decays the standard model via kinetic mixing. So we keep an eye on the time. So in this case, the UV completion we have in mind is introducing a kinetically mixed dark photon. So that gives you an explicit or normalizable connection to the dark current as well as the standard model current, and gives you an effective kinetic mixing parameter that depends on the strength of the coupling to the dark current, this mass ratio, and then the fundamental kinetic mixing. The constraints here that are relevant are on the are on the kinetic mixing, and they come from precision electroweak because the direct search constraints are essentially irrelevant once the dominant branching ratio of the dark photon is not into standard model states. So again, you go through this exercise, you find a lifetime bound, and the portal constraint couplings are now one of the biggest considerations in determining the scale of the lifetime. And finally, one more example, the Higgs portal. Again, in this example, we did something which, if you don't like, you are free to construct your own and more restrictive lifetime estimate. We took scalar constituents here because essentially any option you take is going to be mildly ugly. Either you will have very high operator dimension, or you will have a large CP violation, or you will have to invoke arguments about non-standard, non-QCD-like theories that are poorly understood. In this case, you have a UV completion that is actually more normalizable, but so given, sorry, these should be verifies. So these are the constituents. These phi's are supposed to be the same. So given the Higgs portal coupling here, you actually have two different now contributions to the mass of these constituent quarks, and you don't want them to be large, and you don't want there to be a huge cancellation between the two of them. This is a tree level fine tuning, and if you require light quarks, so quark mass lighter than the confinement scale, and you require that both of these terms, both of these contributions to the quark mass should be smaller than the confinement scale, that bounds the ultimate size of this coupling. And that bounds the mixing angle and therefore the lifetime of the scalar meson. So I show you these models because they give you they all have different theoretical and practical considerations for what's determining the minimum lifetime. The story that we come up with is something that, as a function of the decaying meson mass, what the sort of minimum, easily realizable lifetime is. Again, it's not a hard lower bound. The point of doing this is to understand where high multiplicity signatures are the most interesting, and to help guide development of dark shower signatures in areas where it's easiest to actually construct models that live. So, 1 meter here is the size of the LHC tracker, typically. So if you're looking for, a high multiplicity of meson decays at, mass scales of order 2 GeV, you probably shouldn't be looking for gluon or Higgs portal type signatures. You're best off focusing on photon showers or vector portal type showers, because there you can easily get multiple decays in a detector. If you want to look for Higgs or gluon portal things at say 3 GeV, you're talking about maybe 1 or 2 decays in your detector, definitely not 5. So to make this point more sharply, in say the gluon portal, if you ask what are typical multiplicities of visibly decaying objects in these benchmark models as a function of the visibly decaying particle mass? You can ask, how many decays do you see within 1 meter? And here, within 1 millimeter in the dotted line. So anywhere here, you can get prompt signatures without working hard. And anywhere here, you can get displaced signatures without working hard. The bands here show the 1 sigma event by event variation. Again, you expect large variations in the number of particles event by event because the hadronization, parton-Shauer hadronization process is stochastic. So the orange corresponds to standard model Higgs production. For blue and green, H stands for heavy, not Higgs, and the production is instead through the fundamental pseudoscalar mediator that we introduced for the UV completion of the decay portal operator. So as you might expect, the more center of mass energy you have in the event, the more visible particles you expect. Look for dark shower signatures, and if that means more than 3 particles per event, the answer is yes, as long as your eta is not too heavy. But once it starts getting heavier, you're probably better off looking for single production, pair production. On the other hand, and so this is for the case where everything comes down to multiplicity benchmark. This is
Hello, hello, do you hear me?
I think internet connection is not so good.
we're having internet problems.
Yeah.
That's not good. Can you hear me?
Yes.
Yes, I can hear you, but can you turn your page? Can you change the slide or?
Yes.
Oh, no.
It's portal?
Okay.
Here, okay, yeah.
So could you explain a little bit more about these 2 plots? For example, why, how does, so on the left panel, you show the omega tilde mass is 2.5 times eta tilde mass.
Yeah.
And on the right panel, you show that omega tilde and the eta tilde is the same mass.
Right.
And the number of decays, and they are different. So how does this dependence on the omega tilde and the eta tilde mass?
Good, yeah. So here, the omega can decay into pairs of eta, and the eta is the particle that decays visibly. Here, the omega is detector stable and escapes the detector. Now, the omega is spin 1. So when the 2 particles are degenerate here, you expect just by degree of freedom counting that roughly you get 3 times as many omegas as etas. So this is our low multiplicity benchmark.
I see.
So
and what is the what is the difference between the solid lines and the dashed lines?
Good. Solid lines indicate decays within 1 meter. Dashed lines indicate decays within 1 millimeter. So this essentially demarcates where you can start getting prompt signals without trying hard.
I see.
So this indicates where you can get tracker signals without trying hard.
Okay. Good. Thank you.
So similar story with similar notation for the Higgs portal. Overall multiplicities are lower because the lifetimes are typically longer for the Higgs portal, especially at low mass. for our low multiplicity benchmark, exotic Higgs decays, dark showers is not a well-motivated signature. Even for the high multiplicity benchmark, it may be a bit of a stretch. It would be something worth study to see if you get a lot more mileage out of high multiplicity searches compared to low multiplicity searches here. And then vector portal, we only show this benchmark because here the decaying particle is the omega rather than the eta. And so if the omega can decay to the eta, then there's no interesting signals at all. Because everything goes down to the eta, which is detector stable, and you just make missing energy. So because there's always detector stable particles in this benchmark, the overall multiplicities tend to be lower. But because the decaying particle is the omega, the spin 1 particle, rather than the eta, the multiplicity is not as low as it was for the Higgs portal case over here. So I am somewhat over time, so apologies. These are the conclusions. So experimentally, this is the right time for theorists and experimentalists to be working together to figure out how to design good searches for long-lived particles in general, and in particular, these sorts of challenging high multiplicity signatures that come up with confining hidden sectors. There's both challenges and opportunities. The opportunities are the facts that these signatures are enormously distinct from standard models. The discovery potential, if you can get these things on tape, is very high. If we are so lucky as to find one of these things, we'll learn an enormous amount about the particle physics, and in particular, how to think about the particle physics of confining hidden sectors. It would be amazing. There's a well-motivated generic possibility for beyond the standard model physics. The fact that people worked out perturbative signatures first is not because non-perturbative signatures aren't equally as able to solve problems like the hierarchy problem or dark matter, just because figuring out their signatures is a lot harder. But there are enormous theoretical uncertainties. And in a lot of ways, we are limited by our current Monte Carlo tools. It's really worth taking the time to understand the limitations of the PYTHIA hidden valley model, to think about places where it might be worth going beyond those. And ultimately, the aim of all this work is not to advocate searching for specific BSM theories, but develop a suite of benchmark models that can be used to develop a systematic, inclusive search strategy at the LHC, and in particular the HL-LHC, that will cast a sufficiently wide and flexible net to be able to catch confining dark showers, no matter what they look like. And this is only step 1. So thank you very much for your attention.
Yes, thank you for nice talk. So is there any questions?
Hello, can you hear me?
Yes.
Yeah, thank you for a nice talk. And I have 2 questions.
Great.
The first one is for the dark sector showering and hydranizations, you use the PCR8 hidden valley models, right? And for the PCR8, they use the string model. So
Yeah.
in the future, it's possible there are other tools can also double check this kind of dark sector showering or hydronization.
Yeah. So I'm going to say something which might be a little controversial. I actually think the biggest issue is not going beyond the string model of hadronization,
Yes.
but looking for radically non-standard model-like patterns of evolution.
I see.
Because as long as once we find something, should we be so lucky, then we'll want to really understand the differences in different models of hadronization. But for discovering things, I'm more worried that I will miss a signature in a search if I don't have a generator that is capable of giving me a radically non-QCD-like pattern of energy flow.
Yes.
So I'm not so worried about making sure I have the right variant on QCD for a non-standard model theory, as long as it's close enough that the search, a search designed with the string model will pick up something relatively nearby. I'm more worried that if I have a theory that predicts a lot of wide angle emission that parton showers just don't, I might miss that altogether. Or if I don't have enough hadron species in my hadron model to have enough flexibility to get the right range of multiplicities that I expect.
Wow, okay.
Yeah, so like I said, this might be somewhat controversial. That's my point of view.
I see. My second question is, as you say, if we were lucky, we can discover this kind of spatial dark showering event. And also, if we can also know the mediator mass. So how can we further test this kind of model? For example, is it possible we can reconstruct the eta prime or omega prime resonant peaks or other dark sector parameters?
Yeah. So if you can pick up, say, some of these vertices, then yeah, you would be able to learn the typical track multiplicity in those vertices. You'd be able to reconstruct the invariant mass of those vertices. Some models are easier than others. Models of photon showers are a lot harder to pick up than models with, say, pair of dimuons.
Right.
But yeah, if you got one of these, you would learn so much.
Okay, I see. Thank you for your answer.
Oh, thank you for your questions.
So I have one question. So still we can detect displaced in the LHC.
Sorry, your question is, can we detect displaced signatures
So
of the LHC?
yes, displaced protect signature.
Yeah. So these analyses are hard, but one of the fundamental limitations is the trigger. So especially in run 1 and run 2, most of the displaced object analyses come in on other triggers, often the HT trigger. This is partly, again, historically, a lot of the drive for long-lived particle signatures has been SUSY. And so you're looking for very heavy things. But it's more work to understand the background, and it's more work to do the reconstruction for displaced objects. But yeah, absolutely, you can do these searches. And there are more and more of them all the time.
Okay, and so in Hidden Valley module, so
Yeah.
in this module, so some dark mesons decay to QCD standard particles, right? Okay. So since currently there is no way to make some kind of dark meson decay to some dark particles, so it makes some kind of dark showering. Then in the and consequently this showered dark particle decay to some standard model, and we can detect. So it's this kind of simulation is currently not possible.
No, that's right. That's right. So the closest you can get to that is the situation where you let the spin 1 meson in PYTHIA 8 decay to the spin 0 mesons, because you only have 2 meson species. That's it. Yeah.
Okay, thank you.
Okay.
So again, that's one of the big limitations of the
Okay,
PYTHIA 8 package. Yeah. The Hidden Valley package.
Can I ask a quick question?
Please.
Yes. Yes. Yeah, I don't know much about this topic, so maybe my question is naive. But you talk about the current development and in trying to understand the current MC tools for these showers and displaced vectors. But is there like experimental community effort in trying to analyze this, or basically just like more phenomenologists trying to kind of use the current tools in order to understand it?
Yeah, no, this particular area is of interest both to phenomenologists and now also to experimentalists. So CMS actually already has one search that uses the PYTHIA Hidden Valley module public, and that is this emerging jet study. LHCb has also used the Hidden Valley module to do some dark shower searches. One theme that often comes up in conversations with experimentalists is this theme of understanding that the PYTHIA 8 Hidden Valley module is really in a very different theoretical footing from PYTHIA 8 for the standard model. So being very clear about what we're doing when we use PYTHIA 8 to model Monte Carlo to do experimental searches is actually much more of a headache than I expected before I wrote this paper.
Okay.
This was not what I expected part of the message of this paper to be when I started, but that's where we are.
Okay. Okay. Thank you.
So I have one question about this kind of setup. So you are talking about dark showering, etc. So I mean, I think you have some kind of dark matter in your mind, and so now you have omega tilde and delta tilde both decay back to the standard model sector, right? So in this case, what would be a good dark matter candidate from the darker confining sector? Or are you assuming something else for dark matter?
Yeah, I'm not trying to solve the dark matter problem.
Okay, I see. Yeah.
Yeah. So dark shower, emerged as the sort of standard LHC nomenclature for these signatures, but they don't necessarily include dark matter. This is a very LHC focused set of terminology. So, there's very often missing energy, but there may not be. And whether or not the detector stable stuff is actually cosmologically stable is a model building question that's, for theorists, very interesting, but yeah, not one we're trying to answer here.
Okay. Okay, thank you.
I have a question. So, except for the multiplicity, so other features are highly model dependent, so you didn't deal with about it.
Sorry, other features are highly model dependent. So I missed the keyword. My fault.
So you only consider the multiplicity of the event
for current purposes, right? And that's because you want to know, if you are thinking about doing the hard work of designing a search, you want to know if you should be doing a high multiplicity search for, say, 5 GeV displaced vertices at all. So understanding the truth level prediction for typical visible multiplicities is important for understanding what kinds of analyses should you prioritize developing. So, of course, the next step is to actually ask, okay, what kinds of actual analyses can we do? What kinds of sensitivities do we have? That's the next paper. And that realistically has to be done with experimentalists on board, because understanding the efficiencies, especially at the trigger level for displaced objects, is easy for theorists to screw up. So I personally am much happier if I can get an experimentalist to do it with me. Other people are more brave.
And another question is the long lived particle can also decay inside the calorimeter.
Yes.
So
Yeah, absolutely. I mean, the reason that we're focusing on tracker decays is partly because if you're, again, after high multiplicity signatures, increasing the typical lifetime, stretches things out. And the longer your lifetime is, the harder it is to get many decays in the detector. Now, if I made a version of this plot that cut the solid lines further out in the detector, so you could get muon chamber decays, calorimeter decays, that would also be interesting. But most of the real gain for backgrounds comes when you have tracker level discrimination. And so that's what we're focusing on for high multiplicity. Yeah. So quite often one of these events might have additional decays in the muon system, in the calorimeter. And that's also interesting. Yeah.
thank you.
Thank you.
Okay. So is there any last questions? Good. If not, thank you for your nice talk again. So
Thanks again for listening.
okay, hope to see you meet again.
Thank you very
Bye.
much.
In person.
Thank you.
Yeah.
Thank you very
Bye.
much.
Bye.
Thank you. Bye-bye.